So I recall the thing we want to prove is this isomorphism between the extended affine Hecke algebra attached to the group G check. And I'll stop writing this just for a reminder. And this, we want to show this is isomorphic to the equivariant K-theory of for the group G. So here G bar is G times C star acting on the Steinberg variety. And we explained last time that here you have a convolution product, and we want to show this theorem of Kazhdan-Lusztig and Ginzburg that this is an isomorphism. And I've been started by discussing the structure of the Steinberg variety last time. So we recall that flag variety is G mod a fixed Borel. And then, so the Steinberg variety is T star of flag times T star of flag with the map to G. So maybe I recall everything. So T star of flag, this map can be identified with elements of such a pair. So where X belongs to the radical of B prime, I'll just write M prime, and then B prime is an element in the flag variety. Okay, and then this map is given by sending such an element to X. So sending this to X. Right, and so it projects in particular two copies of flag variety. This is a G equivariant map. So let's call it P. And then we have seen that the diagonal G orbit in the flag variety is indexed by elements in the Weyl group. So here, this is a disjoint union of, so last time I used O, and then there was some confusion, so I decided to change my notation. So where FLW is consists of, let's say, B1 and B2 in relative position W. And we have explained that Z of W, which defined as the pre-image of this orbit, this is actually, via P, this is actually a vector bundle over flag of W. Okay, and so moreover, since the closure of flag of W is union of elements smaller or equal to W in the Breuer order of the smaller orbits, and so if we denote Z smaller equal to W to be P inverse of this closure, this is a closed subvariety in Z. And so we can consider the following situation. So we have a closed embedding of, I hope the notation explains itself. So this is the union of ZV for V strictly smaller to W. And then, so this is closed in Z smaller or equal to W. And then here you have an open part, which is our ZW. Okay, and everything is G equivariant. And so by Devisage, which I mentioned last time, so you have, so this yields a long exact sequence in K-theory, so of Z I star kg 0 of Z smaller equal to W, and then you pull back by K Z G Z W. And as I was told last time, I made a mistake, and I indeed made a mistake. So here you should have so the long exact sequence looks like this. You have some higher K group ZW, which is not trivial, even though ZW have a paving by affine spaces, but this property allows you to say that the restriction map from Z, so this map is always surjective, and therefore therefore this map is 0, so the sequence split, and so this uses that ZW is vector bundle over flag W, which has an affine paving. Okay, so anyhow, from this we get a short exact sequence in K-theory, and this tells us, so this gives us a filtration on our algebra by such terms. Whose associate gradient equal to just isomorphic to, so on the associate gradient ring, you do the quotient of this by lower terms, and then by this short exact sequence, you identify it with this. So this is isomorphic to just kg of this ZW. Okay? And now, this we know how to compute because we explained last time that so ZW is a vector bundle over the orbit. So by Thom isomorphism, this is isomorphic to kg of this orbit. Okay. And then we explained that this orbit under the isomorphism, maybe I put here. So remember we had this isomorphism that this is isomorphic to G mod V of flag, where there's this orbit, flag W corresponds to G over B of B, WB over B. Okay? So via this morphism, you can view this as an induced variety. And so using induction, as last time, we see that this is KB, this is just KB of BW, maybe times C star, BWB over B. Okay? But this is a B orbit, so at the end, this is just the same as taking the stabilizer, which is T times C star of just a point, this point, WB over B. Okay. So in particular, as a ring, or as a module over the equivariant, over the character ring of the torus, this is just RT. So T is this group times a certain class Yeah, which I will not write. Okay. And so this tells you in particular that, so you can trace back this map and then under this identification, if you have an element here, it basically just goes to more or less f times the just the class of the structure sheaf on this ZW. Okay. And so, okay, so what we learn from this is that and everything is an isomorphism as left RT module. Okay. No, it's just so when t goes to there's a quotient by b. Yeah, okay, yeah, right. So stabilizer can be bigger, but the other parts are unipotent, so I can reduce to t. Thanks. And sorry? RT is the character ring of T. So this is you can write it as KT of a point, or just the Grothendieck group of representation of T. Yes? This is B times C star. Other questions?
Upon theory was that from last time that you showed that the algebra is contained in the table, but it didn't.
I'm not talking about the proof yet. I'm just first, I want to discuss a bit about the structure of the right-hand side, which will be used in the proof, and then I will go into the proof. Okay. Other questions? Okay, so you have a filtration by RT modules, and each of the pieces is just isomorphic to RT itself. And so from this, at least, you see as the size of the module, this thing has the correct size. Okay, so this implies in particular that Kg of Z is a free RT module of rank W. Well, I was using WF before, so. Okay. Okay. So and we know that Hecke algebra have a basis indexed by x lambda and tw for w in WF, and the x lambda span a subalgebra which is isomorphic to RT, and so at least from this you see that two algebra have the same size. Okay, now I want to talk. I still need another preparation before I go into the proof. So the other ingredient I will need to, so you see I explained last time that we want to identify both algebras using polynomial representation. And for this purpose, you need to compute explicitly some of the generator of this algebra. How does it act on the polynomial representation? So you need some tools to be able to compute with this equivariant K-theory. And the tool we're going to use is the so-called localization theorem. So where is the best place to write? Maybe I write it on the side so that I can keep it. I don't know. So this is a quite general theorem on on equivariant K-theory. So suppose you have an algebraic variety X equipped with a torus acting T acting on X. And then, so you consider the embedding from the fixed point in X to X. And the push forward, so this is closed, and so the push forward induce a map from T equivariant K theory of the T fixed locus to the T equivariant K theory of.
What's the action of acting on each?
Oh, the module structure, there are several ways of saying it. You can, if you have a T equivariant sheaf and you have a representation of T, you can always tensor it and get another equivariant sheaf, and that's the action. Mm-hmm. What? Yeah, if you, yeah, right. If you go, okay. Oh my God. Yeah. So I was explaining. Yeah. Okay. Right. Yeah. Indeed, I was lying a little bit. So the RT module structure here is what I just explained. And moreover, I think if I want to be completely correct, I need to do it on the right. And then indeed, as what Liang-Shi explained, you need to, if you go through this, you need to consider the corresponding induced bundle on this, and then doing the tensor product with that bundle. Yeah. Okay. Other questions? Yes. Say again? Yes. I think so, yes. Yes. Yes, yes, yes. Yeah, maybe I went a bit ahead of myself by discussing this first, but yeah, maybe I should have discussed it later. So it's more natural to see it as action on the polynomial part inside the Hecke algebra, but yeah, but anyhow. So I was talking about localization theorem, and so the theorem of Thomson says that this map is an isomorphism after localization. So what does it mean, localization here? So in this setting, both are modules over RT in the proper sense I just explained. So this is a morphism of RT modules. And we just let KT equals the fraction field of RT. Okay. And localization means you just you just base change to KT. So i.e. that the map from kt of xt. Answer RT. Oh, I have so many Ks. Oh my God. Oh. FT. That's a good idea. Oh, let me just do frac RT. It's isomorphic to kt of x. Okay, so in particular, this tells you that if you're so in particular, if kt of x is torsion-free over RT, then it's embedded in its localization. So then we have kt of x embedded into kt of x localized. So I'll use the notation that this I will just replace it by log. Okay, log means phase change to the fraction field. And if torsion-free, this localization is still injective, and by this isomorphism, it's isomorphic to kt of xt. Okay. And so this map, so this is like the inverse of I lower star. So this map, I would denote it by I lower star inverse. And in many good situations, like in the situations we're going to consider, that when you have the fixed points are isolated, let's say P1, Pn, so isolated fixed points. And if your x is smooth, then this map can be computed quite explicitly because so what is this? This is kt. So the map is kt from kt of x. It gives you an embedding into this guy, but xt is just a bunch of points. So this is a direct sum over I equals to 1 to n of the fraction, so of kt of this point pi localized. Okay, this is just a copy of fraction field of t. And now if you have a class of sheaf here, what is the image under this map? And this is the place where you use the Thom isomorphism we discussed yesterday. Remember, we discussed that if you have a smooth manifold embed in M, let's call it iota, and I explained if you do iota push forward and pull back, this is multiplication by the Euler class of the conormal bundle on the K group of n. Okay, this is what we explained last time, and here you just apply it to the situation that pi, that you just have a point embedded into the smooth variety x, and so but we're doing inverse of I lower star. And so this map, the image of such an n on the right-hand side is the sum of I equal to 1, from 1 to n of 1 over the Euler class of the cotangent fiber of x at pi, and times just the fiber of m at pi. Okay. So this is something very explicit because just try to fit everything in the same board. Because the t of so remember t pi is a fixed point. This is just a representation of the torus t. Oh, okay. Thanks. This is just a representation of the torus t, and so for such a representation, actually for any representation, let's call it V. What is this class? This class is just you. This class is just you decompose this V as eigenspaces for the action of the torus. So it's indexed by some by the character of the torus. So it runs for alpha belongs to x star of t of some v alpha. So these are some weight spaces, and then this this lambda of such a v is nothing but 1 minus. You cannot read. Okay, sorry. Yeah, I'm trying to be too optimistic. No worries. Right here. So maybe I first finish here and then I'll write it again. So it's minus alpha of dimension of v alpha. I take the product over alpha. Okay, I'll write it again here. Maybe just write for V, a representation, you just need to remember, for V, which is a representation of T, so this, you decompose it into weight spaces according to characters of T. And then if you do the computation in this particular case of the Euler class we defined yesterday by taking causal resolutions, etc., you will find that this lambda v is equal to the product of 1 minus e to the power of minus alpha times dimension of v alpha. Okay? This is something we'll use later on. So all of the points here is just to show you that in the situation where your variety has isolated fixed points and it's smooth, this map can be computed quite explicitly. It only requires you the knowledge of the weights on the tangent space or cotangent space at these points. Okay. Okay, now we're in business. So we want to prove this theorem, and our strategy, I recall our strategy was we have explained that we have an action of extended affine Hecke algebra on the polynomial representation, which we have identified with the G equivariant K-theory of the cotangent of flag. And then we explained by convolution, this receives an action of our algebra, Hg of z. And this was my action, algebraic action. This was my geometric action. And I want to show that, so the claim to prove is that first, rho G is injective. And second, image of rho A belongs to the image of rho G. Okay. Okay. And we can do all of that through localization. So rho G comes from a map which you take Kg of Z. So it's an action of this tensor over C, Kg of T star of flag. And so here is the action map to Kg of T star of the flag. Okay? And to reduce to a situation where we want to localization theorem, you can first forget from the G action to the T action. And this is actually an embedding. So all the thing on the top embeds into Kt of Z times Kt of T star flag to Kt of T star of flag. Okay. And we have seen that this range just RT itself, and then this is free over RT. So everything here is free over RT. T star flag, just free over. So I can just use this Thomson localization theorem and get an embedding of everyone inside Kt of Z fixed T fixed point times Kt of T star flag fixed points, and this goes to Kt of T star flag fixed point localized. Okay, and everywhere this map is, I would just write I everywhere without distinguishing the variety. So this everywhere is induced by this inverse of the push forward of the fixed locus. Okay. So now what are the fixed points? First of all, on cotangent of flag, you observe that this T is what? It's T, the maximal torus. So this is the maximal torus times the C star, where C star dilates the fiber here. And so if you take the fixed points, then the C star fixed points will stay in the flag variety itself. And now the T fixed points in the flag variety is just the index by the vowel group. Okay. So this is nothing but a direct sum of Kt of, so I would just write W log for W in W. And so we have the same thing here. And here, if you look at that map, you realize the again, the C star acts on the fiber direction, so all the fixed points stays in the two copies of the flag variety, and therefore the fixed points is just 2 copies of WF. So this thing identifies with direct sum of W and W prime in finite vowel group of KT of a pair of elements W and W prime. Okay. So we're in a very nice situation now because, there's a tensor product. Because this is just a vector space with the basis indexed by the vowel group and with coefficient in the fraction field of the character ring. Okay, so it's a vector space. And here we have an action by convolution. And this convolution will induce you a convolution product just by transportation of structure. It will induce you, so this is nothing but localization. So this gives you a map here. And the problem is you want to compute this map. Okay? So what is this map? Let's try to arrange my boards. So I gave an exercise 2 days ago. If you do like convolution on functions on a finite set, 2 copies of finite set, what do you get? You get matrix multiplication, thank you. So here we're basically in the situation, right? We have this, except it's the matrix acts on a column. So it's a matrix with rows and columns indexed by WF. And if you do the convolution, you will just get something like the matrix multiplication, except it's not as easy as that because so maybe let me first start by saying it's not so hard to observe by the definition of convolution if I do maybe just to avoid confusion, I will write delta W prime as the function which is just like 1 on this. So I will view this as the base point in this ring. Okay. So and similar for the other. So naturally, you just by definition of convolution, you will see that if you convolve these 2 things, so if you do with delta of W double prime, then this is basically matrix multiplication, meaning that, delta is again a horrible notation. But okay, I'll write it. So this is equals to, if you do matrix multiplication, this will equals to delta W if W prime equals to W double prime and 0 otherwise. Okay, but it is not quite that. Do anyone know why? Yeah, so because, yeah, you can say it that way. But you remember in the first day when we're talking about convolution product, we say we pull back classes in K-theory to the top. So you remember on the first day I had this diagram. I said we will need to work with some smooth varieties, and then we view our Z as subvarieties inside here. And in particular, when you're doing the tensor product, you need to do it inside this smooth space, not just on the points. Okay, so for this reason, when you're doing this tensor product, you just pull back skyscraper sheaves on your points. You pull back them to three copies of T star of the flag. And what is happening here is that when you're doing the tensor product, you're doing it at the point W prime inside the cotangent of the flag variety. So here there's an Euler class of T star of W prime of this flag variety is coming out. So I will write from now on x equals to T star of flag, just to avoid having so many T stars everywhere. Okay. So if you really trace your definition of convolution and does the computation through this diagram, this is the multiplication you get. Okay. Okay. So this is one important point, but nevertheless, now we have a rule to compute after localization this action of this algebra on this polynomial representation, and okay, and it's fairly easy to see that. So here we just have a matrix algebra X on the column with some modification of the coefficients. So the vector space representation of a matrix algebra is faithful, just for a tautological reason, and so therefore so from here we see that this star is a faithful action. And since all the vertical arrows are injective, this implies that implies that the action of rho g is faithful. Okay, so this proves the first part of the claim. And now we need to do the second part. So for the second part, we want to show that image of rho A ends in image of rho G. But we know that this algebra is generated by Ts and x lambda for lambda in the character ladders of T, and S is a finite reflection. So it's enough to show that the image of these generators belongs to image of rho G, because all the maps there are algebra homomorphisms. So x lambda is kind of not too difficult to see, because you so what you can do is in kg of z, you have in particular the orbit of 1. So this is by definition the diagonal orbit inside the Steinberg variety. So this thing itself is isomorphic to kg of cotangent of the flag variety. Okay, and therefore you can define so for every lambda, which is a character of T, we can define a line bundle, let me call it O lambda, which is given by G, the induced bundle where you put the character lambda at the point 1. Okay. I could be off by a sign, but I don't want to care so much about the details. So this, okay, so, sorry, you take, this gives you a line bundle on the flag variety, and then you pull back it to the cotangent bundle. So let me still call P, so T star of flag to flag, and then you do pull back of the line bundle I just written down. So here, the unipotent radical of Bx trivially and Tx by the character lambda on this vector space. Okay. And then you view it as a so you consider its class inside this equivariant K-theory, and so you identify it as a class on the diagonal orbit, and it's not hard to see that if you when you consider the polynomial representation, so O lambda action on so O lambda action on this. Let's see, how should I write it nicely? Yeah, so basically under the identification of polynomial representation and Kg of T star, it's not hard to see that the action of this thing, so rho G of this, identify with rho A of multiplication by x lambda. Okay.
So why is that conclusion?
What is this line? Why is this an inclusion? Because this is the closed orbit. This is the identity element. This is the closed orbit. Yeah, but that's a good point. Thanks. Yeah, so basically what you say is just you identify the polynomial representation with Kg of T star of the flag, and then you're doing the convolution by the diagonal orbits, and so if you trace back to all the identification we have made, this just becomes the multiplication of Chern classes on Kg of T star of flag, and so it's this is not something difficult, and but you need to trace the signs, etc., which is painful, and I didn't do it. But more interestingly, what you want to understand is the action of Ts. And so for this, you have some sort of natural candidate, because you know your algebra have a basis given by, you have that kind of stratification given by ZW, so this Ts must have to do with the simple reflection S. And as we explained, so naturally you're looking at this ZS, the part which is indexed by the simple reflection S. And this, as we recall, this lives over FL of S. And so what does FL of S look like? This is G over B of B as B over B. Okay. But when you consider K-theory classes, you need to take classes on some closed varieties. So so you want to work with the closure of this this orbit, and then we know that it is given by just a union of this with B over B. Okay. So this in total, this is a copy of P1. It's the flag variety for the minimal parabolic corresponding to S. But on the other hand, if you take our projection from, which I also denoted by P, if you take this projection, I explained last time how does this look like. This is an induced variety, but well, I explained for SL2, but you get the idea. So on this copy of the orbit, it is given, the fiber is given by the intersection of the neoradical of B intersection with S of N. Okay. Well, actually, if you find it difficult to following now, you can just restrict yourself to G equals to SL2, and you don't miss anything in the discussion. For SL2, this is just 0, and so over this part, this variety is just this vector space. But over But over B, you get something more. So it's, yeah, I'm just not doing my pictures very nice. So yeah, maybe you should think of this as a union of an A1 and then union a point. And then what I'm saying is over this A1, this fiber is N intersection with Sn. And over this point, this is the entire N, okay? And so, again, in the example of SL2, this is a variety which looks like this, and you have a line here. And this is not something smooth, and you don't want this, because if it's not smooth, it's hard to compute its, you can always define it, but then it's hard to compute its image in K-theory under the localization theorem. So instead, what you can do is you take first the pre-image of the open cell. So you take P inverse of FLS. And then you take its closure inside ZS. Okay? So in this picture, it means first you just take this part, and then you take its closure, so you just get to P1. Okay, this is something smooth, and yeah. So here I have something inside G over B. No, this is like isomorphic to two copies of flag variety. Okay, yeah. But wait, was this my notation? I forget my notation. My notation FLW was, yeah. Okay, so the point I want to make is that this is properly embedded into P inverse of FLS closure, but this is something smooth. That's the point. Okay, and let's give it a name. I think I'm running out of names. What did I call it? I think I called it ZS, but then now I use ZS for other purpose. Yeah. Good name. So, X is like I call it YS. Okay. So, all right. Okay. No. This is the second one. So the proposal now is to compute just the structure sheaf on this ys, and see from there you can get a generator of the of this Hecke algebra TS you were looking for. And with all the tools I have explained, we have a way to compute this class of ys. So now we want to compute the class of OYS. And so you want to compute how it acts on the polynomial representation. And so you know the trick now. You just first localize everything to the fixed point. And then on the fixed point locus, we know the multiplication rule for the algebra. So to compute this action, I only need to know what is the image of this thing under the localization map. Okay? But this you also know because this is the way how you compute it. So first of all, its image inside the localization, it supports at the fixed points of this thing. And what is the fixed point? So this should be equal to the sum of so it should be equal to the sum of W in WF of delta of WWS. So some coefficient plus some coefficient of delta WW. Okay, because if you read over there, so in the definition of ys, in the first copy of G, you have fixed points which are indexed by vowel group, and then in the second you have either S or identity. And therefore, you only get fixed points of these two types. And to compute what the coefficient here, you need to compute what is the conormal of this fixed points inside, what is this cotangent fiber of your fixed points inside that variety ys. Okay? And so here this is the inverse image of lambda of T W WS star of ys, and here I put lambda of T star WW of ys. Okay, so let's see, what are the cotangent fibers? So if I just look at the tangent space, it's kind of easy to describe. So maybe I put in here again my ys is, so my ys is basically G times B times this P, so PS over B. And then on it, I have a fiber which is times this fiber, which is n times Sn. Okay. This is the ys we have defined. Okay. So this part goes away if we're in SL2, but if it's not SL2, this is a vector space which stays. And then on the other part, you have this. And so what is the tangent space at the point where here you take, if you want to this, you take the element W here and you take the element S here. And so here the tangent space is the negative of the opposite potent radical. And over S, this is given by, so plus n alpha S. And and plus this term, so n of plus n intersection with Sn, And I think everything should be twisted by a W. So yeah, so say again. No, it's no. I'm taking. So if the conormal bundle part appear if I embed ys into the cotangent of flag. Conormal bundle. I don't understand why do I need conormal for FLS bar? Okay, so I don't need that part because so yeah, I omitted something. You're right. So what you need to do is you need to first push this class to the entire cotangent of flag times flag, and there this class involves. But then when I doing the restriction back, that part just cancels itself, and so I only need to compute how this fixed point is embedded into this smooth variety. Yeah. Yeah. So I think what I'm saying is correct, but let me check my notes. So Wn minus n alpha. Yeah. Okay. Okay. So you see, you get a space like this where you can compute explicitly the weights. Okay. So I told you. So now you want to take the dual. So you take the dual of this space, and to compute this class, you just need to apply this formula here, and then compute the torus weights on this vector space. But this is something explicit because this is a sum of root vectors, and you know how it acts. Okay, so this is just I will not write down the computation, but this you can do. It's very explicit, and then TW W star of ys is the same thing, but here you take n of minus alpha s plus an intersection of Sn, and you take the dual. Okay, and so now you can compute this, and you can also compute the inverse image of our generating like this diagonal or this line bundles on the cotangent of the flag variety, which corresponds to this elements. So this corresponds to this elements E alpha in the polynomial representation. And so this is just given by the sum of W in WF, and then here you put a lambda of cotangent of W inside the cotangent of the flag variety times E of W lambda. Okay. So this is just, you restrict this line bundle to all your fixed points. This gives you this. And then you multiply by the corresponding Euler class above. And in this way, you computed the image of these things inside this matrix algebra in the bottom. And I gave you the rule of this matrix algebra, so you can compute explicitly how OYS acts on an element like this. So the computation from this point on is everything is explicit. So if you carry it out, you will get that at the end, the action of this O of ys, so rho G of this class is equal to rho A of Ts plus 1 minus Q times 1 plus e to the power of 1 x alpha s, something like this. or minus affine. Okay. Okay, so so you get such an element in the image of row A, but we know that all the polynomial parts is already in the image. And so therefore you show that the image of TS indeed belongs to the image of row G. So this shows row A of TS belongs to the image of row G. And so we are done with our claim. So this proves part 2 in the claim. Okay. So you may feel puzzled that why, if you have some experience of these things, why you have a class like this, why you don't just have TS plus 1. This is, actually you can do this thing better by, instead of taking the structure sheaf on the P1 component, if you take the canonical bundle on P1, then you will get a nicer look class. But for our purpose, it's not so important. All I want is just to show that the image of TS belongs to the image. Okay, so at this point, we have shown that so at this point, we have proved this claim, and therefore, we have shown that this diagram factorizes. So this is injective, and this factorizes and gives us an algebra homomorphism. From the extended affine Hecke algebra to Kg of Z. Okay? And now you want to show this is an isomorphism. This is not so difficult using dévisage. So we have phi from Hx to Kg of Z. And here we can define a filtration by, so set smaller equal to W by by the span of, so you take RT times an element TV for V is smaller or equal to W. Okay, and then and this defines, because these kind of things form a basis, and this defines a filtration on this algebra, and then you need to use your knowledge about TS we have just shown and use some not so difficult property of convolution product to show that phi restricts to from Hx to this Kg of ZW, and therefore it induces a map on the associate graded. So, and on the associate graded ring, so we just get, so on the left, we still just get a vector space, RT, times the image of this TW bar in the associate graded. And on the right-hand side, we get this W in WF of kg of this, I'm sorry, this was smaller equal to w, and then of zw. Okay? And then, yeah, and then you have to show this. Now I can come back to this RT module structure. It actually just comes from this actions of this line bundle on the diagonal on the equivariant K-theory of Z. And we have shown that these two are identified as RT module. And so this is an isomorphism. And therefore your phi restricts to so it's like have filtration by free RT modules, and it restricts to an isomorphism on the associated graded ring, and each of the pieces just rank 1 over RT. And so this is enough to imply that phi itself is an isomorphism. Okay. Yeah, so I'm skipping many details here to show many like compatibilities with convolution products, etc. But it's kind of formal, and you get the idea from this argument. Okay, any questions? Yes, yes. Thank you. Yes. Water. Okay. If everybody is good, we can now move on to discuss consequence of this isomorphism. Like one of the consequences is you can use this to study representation of a affine Hecke algebra using some geometric construction. So classifications of irreducible representation of extended affine Hecke algebra. So on the first day, we have seen that the center, so now this stands for center, inside of this extended affine Hecke algebra identifies with this invariant polynomials in this Laurent, in this character ring. Okay. So it was not completely written in this form, but so this is the thing generated by QQ inverse and all the X lambda and take invariance by the finite vowel group. And this is the same by Cholet isomorphism as the character ring of G. And so this just sits naturally inside Kg of the Steinberg variety. Okay, any equivariant K-theory is an algebra over Kg of a point. It's a module over Kg of a point, but in this case, I show this is the center here. So now, if you for any irreducible representation L of H extend, the center acts by a scalar. I mean, any central elements x by a scalar. Elements x by scalars. And so this is just short lemma. And so in particular, from this identification, you can see that so a central character, so chi, the central character of this is equivalent to just choosing a point in spec of this ring. So like a close point here, and we know this is function. This has already appeared in other talks. So this is equivalent to a function on the adjoint, the quotient of G by adjoint action, good quotient. And so a point here is the conjugacy class. So a point here is the conjugacy class of a semi-simple element with an element in C star. So my G is G times C star, and yeah, maybe I should write it better. So this is sorry. So this should be like this, and this identified with the space of A equals to ST, and S is semi-simple in G, and then T C star. Okay, and then up to G conjugation. Okay. Okay. Now on the right-hand side, so therefore we can just partition irreducible representation of a Hecke algebra according to their central characters. And so we're reduced to look at representation of this algebra specialized at the central character A. So I just write CA for the corresponding central character. And denote this algebra by HA. Okay? So just a remark that we know that this is free over the polynomial part of rank equal to the cardinality of the finite vowel group. So remark. So this is free over RT of rank WF. And then RT by Chevalier theorem is free over RT WF invariant of rank WF. And so in total, this is a finite dimensional algebra of a dimension WF squared. Okay, now what does this mean on the K-theory side? So on the K-theory side, if you look at, so we're looking at CA times over this character ring of G, which we interpret as kg of a point, and with this kg of the Steinberg variety. And this, again, you can use localization theorem to show that this, so since you have specialized to A, this is the same as taking CA tensor with the just character ring of the subgroup generated by A. So that A be the closed subgroup generated by this element inside G times inside G. And then you consider its representation ring, and then this is Ka of Z. And this is some kind of torus, and so again, using localization theorem, this can be identified with Ca times Ra times Ka of Z fixed by A. Well, actually fixed by A. So here you localize, but since like A is kind of a generic point in this torus, you can choose A to be a generic point. So you can evaluate your, it is possible to, it makes sense to evaluate your character at A, and then you still get an isomorphism. This is not so trivial, but if you want to read this, you should read Ginzburg chapter 5 around the end, where he explained this. So, so since we have specialized the equivariant parameter, this is just the same as the equivariant, non-equivariant K-theory of ZA, and then by some sort of Chan character map or like modified version of it, you can identify this with the Borel-Moore homology of ZA. So this means the fixed point by A in Z. Okay. So so this argument reduces the study of this affine Hecke algebra to those with specialized central character, and those you can interpret as using, well, actually you can either use K-theory or Borel-Moore homology, but there are certain advantage of using Borel-Moore homology because you can use some sheaf theory to deal with this, but this goes beyond the scope of my course. I will not talk about it. But nevertheless, I want to explain how to construct representation here. So try to arrange my board first. So on the very first day, we have seen that if we constructed our convolution algebra, and for us we have this type of Z is the fiber product of some smooth variety X over Y, and then you can have the equivariant K theory of such an algebra acting on equivariant K theory of X times Y for some Y prime, which is a G invariant subspace in Y. So in particular for Steinberg variety, so we have T star of flag times T star of flag over the nilpotent cone. And so my Y is this nilpotent cone, and so for any nilpotent orbit, I can consider, so I can take Y prime just to be the orbit of this element, and therefore, and then this X times Y prime of G X is nothing but just the pre-image of this nilpotent orbit under the Springer map. Okay. And so this is a G variety, and then so by this construction, we have an action of Kg of the Steinberg variety acting on a Kg of this pi inverse of Gx. The nilpotent orbit is conical, so it's stable under the C star action. And this is, again, by induction, this is the same as taking the centralizer of the equivariant K-theory for the centralizer of this X, and then consider the pi inverse of X. And this is the so-called the Springer fiber. So so my pi was from T star to flag to N. This is often referred as the Springer map. And what is fiber? The fiber at an X is just, by our interpretation, is just all the Borel containing this given X. So it's a not what?
I mean, the product of X with the nilpotent orbit is over the nilpotent cone, right? Not right prime.
Oh, yeah, thank you. Yes. Yes. Okay. And so now this tells you, just by advantage of this geometric construction of this convolution algebra, you naturally have its action on the K-theory of Springer fibers. As you vary the choice of this element X, it gives you some representation of this affine Hecke algebra. And now you want to specialize, you fix a central character, so you want to specialize yourself to the A fixed locus. So let's look at what are the A fixed locus. So the A fixed locus in N is just, by definition, our A is a pair of elements with S is semi-simple and T is a scalar. And Sx on nilpotent element on the nilpotent cone by a joint action. So this is X belongs to N such that Sx S inverse is given by T times X. Okay. And now you so you take the fixed point in the you take the fixed point inside the Springer resolution, and so like this, and so this is the, so we first, this is the pair of elements X and B, such that Sx S inverse is Tx, and B is fixed by S. That means S belongs to B, and it also fixed by and also, like in the definition, we had X belongs to B. Okay. Right. So let me, for a given X, let me call this so So let me call pi inverse of x fixed by a to be b x s. So this means so for all the x belongs to n fixed by a. Okay. So this is this variety here. It's the Springer fiber, which consists of Borels and then fixed by s. Okay. And then the same construction here, if you specialize to this point A, it gives you an action of this homology of z of a acting on the Borel-Moore homology of this bxs. So in this way, you construct some representation of this affine Hecke algebra with the central character a, and moreover, on this space, you have a natural action of the centralizer of both x and s. So you still have cxs, the centralizer in G of the pair x and s. So it was more or less here, and yeah, I mean, this is centralizer of x, but when you restrict to this, you get an action of this centralizer. And then the claim is that, so first of all, when you have a continuous group action on some cohomology theory, then the connected parts acts trivially, and so this action, this acts on h of b x s. And the action factorize, maybe let me say, the centralizer acts and the action factorize through the component group. So cxs is cgxs quotient by the connected component. Okay, and moreover, this action commutes. Action commutes. So cxs action commutes with the Hecke action. And so you have a pair of commuting action, and you want to get irreducible representation for the Hecke algebra. Therefore, you just need to take isotypic components for irreducible representations of CXS. Maths. Sorry. Okay, I try to finish. So now, for any irreducible representation of this component group, you can take its multiplicity space inside that Borel-Moore homology. So then you get something which is a representation of the Hecke algebra, and this depends on the choice of Ax and this parameter k. Okay, and so this is an HA representation, which is not irreducible, which is called standard representation. And then you need to construct some sort of dual standard representation with which you can show that it has a simple quotient. So it has a simple quotient as HA module. So simple quotient. So in this way, you obtain some simple representations for the affine Hecke algebra, and then the theorem of Kazhdan-Lusztig. Sorry? Yes. Yes. Kazhdan-Lusztig is that if T is not the roots of unity, then this class of L, A, X, K, where you take into account of this, modulo conjugation class on this triple. So modulo, like, you have those which are G conjugate, they naturally provide the same irreducible representations. And the point is, if they're not conjugate, then they provide different one. And this provides a complete list of irreducible HX representations. Okay, and I stop here. Thank you.
Any questions? Not now? Oh.
Okay. Just I didn't follow some part of the argument when you identify. So first, when it's on the top board, there is a morphism between the specialization at A of the A equivariant K-theory of Z and of the fixed point. So it's like
yes.
Because both are lattices in the same localization. Or do you need to use that these are free as a
yes,
modules?
yes, yes.
And last, why is there an identification between the K-theory of ZA and
the Bohr-Moore homology?
Yes.
This is some sort of Riemann-Roch isomorphism. So in cohomology, you can just use chain character map,
Yes.
and this gives an isomorphism. Yeah,
This is
and
the
in
isomorphism.
homology, you need some different version of it, but it's the same idea. Yeah.
Okay.
Like Gordonic Riemann-Roch isomorphism. Yeah.
Thank you. The structure sheaf of OY.
Under the form isomorphism, I don't know how to get this formula. Oh, sorry.
Under which isomorphism?
Under the term isomorphism.
Yeah.
I actually don't know how you get this formula that like I upper star minus 1, I upper star inverse is OYS is so some delta W primes.
Oh, the computation of the class of OYS?
Yeah.
I will explain it in the question and answer section.
And a simple question, just I didn't follow the definition of NA. Like,
NA is just a fixed point by A in N.
oh, okay. Yeah, thanks.
Any other questions? No? Well, shall we thanks to the speaker again.